Hello, my name is Deniz Sönmez. I am a computer engineering student at Bilkent University. Today, I will be presenting you my Physics 102 laboratory final project, the impedance and resonance in series RLC circuits. The main objective of my project was to investigate how a series RLC circuit driven by an AC source responds to changes in frequency. I wanted to observe the resonance point, the specific frequency where the circuit allows current to pass most easily, and how the impedance behaves around that point. Additionally, I tested how adding an extra resistor affects the resonance curve through the increased damping. For this experiment, I used a function generator, a true RMS multimeter, a 33 millihenry inductor, a 100 microfarad capacitor, and a 100 ohm series resistor. After setting up the circuit, I took measurements across a frequency range from 60 Hz to 1 kHz. When analyzing the data, as expected, the impedance was quite high at both low and high frequencies. However, something very clear happened when the frequency reached 150 Hz. The impedance dropped to its minimum value of approximately 170 ohms, and the current reached its peak at 0.06 amperes. This point represents the natural experimental resonance frequency of my setup. In the second phase, I added an extra 100 ohms resistor to the circuit to observe the damping effect. After reanalyzing the measurements, I encountered a result that perfectly aligns with theoretical expectations. The resonance frequency remains stable at 150 Hz. This confirms that the resonance point does not shift with resistance. However, due to the increased total resistance, the minimum impedance jumped to 268 ohms, while the maximum peak current dropped to 0.038 amperes. These results demonstrate that increasing resistance doesn't move the resonance frequency, it simply suppresses and flattens the resonance peak. As you can see in the graph, the blue line represents the base state of the circuit. As the frequency increases from 60 to 150 Hz, the impedance drops, reaching its minimum level 170 ohm at exactly 150 Hz to form the expected dip shape. As the frequency increases further, the impedance starts to rise again. And the red line shows the condition where an extra 100 ohm resistor is added to the circuit. The resonance frequency 150 Hz has not changed at all. It remains perfectly aligned with the vertical gray dashed line. However, due to the increased resistance, the entire curve is shifted upwards and the dip point has become slightly damped. Finally, I would like to discuss the deviations in my results. While the ideal theoretical resonance frequency calculated using the formula was 87.6 Hz, my experimental measurement was 150 Hz. This high error rate of 71% is primarily due to the fact that the laboratory components are not ideal. Real-world inductors have their own internal parasitic resistance, and capacitors in particular can deviate significantly from their labeled values. Furthermore, taking measurements in discrete frequency steps rather than a continuous sweep may have caused me to slightly miss the absolute mathematical peak.